one cookie. There's a steady way.
Hello and welcome back to Calculus 3, section 12.8, minimum and maximum problems. So we are always interested in optimizing so that we can find the maximum efficiency, maybe to find the minimum cost, maximum profit, right? There are maximum height. So there are many reasons why we would want to optimize. We learned optimization in Calculus 1, where we simply said that you have an equation that you are going to differentiate, and then that equation will be equal to 0, from where you can solve the equation, get the critical points, and then examine those critical points, whether they're min or max, and you are done. We are going to have the same procedure in Calculus 3 now, except we have multiple variables, so we will be using partial derivatives instead of regular derivatives, and we will be doing the same thing as to set everything equal to 0, and then compute the critical points. And now for testing is going to be much more convoluted, because we also learned of the existence of the third type of the point other than min and max, and that one is called saddle point. Very good. So now we have to be on the lookout for which of the three cases we have. Now our method is also going to fail in certain case, so we have to be also careful about that.
Oh, I know.
There we go. Beautiful. So now, if you look at the sphere, at the ball, right? The sphere is going to have the north pole, which is the most north point that you can get, and that one would be the maximum for the sphere. You also have the south pole, which is the most south point that you can have on the surface of the sphere, making that the minimum point for that particular shape. Now, what I can also do is have some irregular shape that is explained through some x and y on some region, and then I can explore minimum and maximum, and also the saddle point on the shape that might look like whatever I made here with this microfiber cloth. So now we are going to take a look at the procedure. So we are going to again define the absolute maximum and the absolute minimum as the two that are either the highest point of all points in a set or the lowest of all points in a set, and then have the relative or also local min and max when they have. Now, the fastest way to actually understand this is to just look at good old Calculus 1 graphs, and then just imagine this in 3D. So what I'm going to do is draw a function, let's say f of x look like this, and now observe this point over here is called the relative max. This one over here is the absolute max. And this one over here is the relative or local minimum. Now, this one over here is a relative max because there are infinitely many points that are higher than this relative max. Now, why is it called max? Well, in its own, right, relative to its own surrounding, it is a maximum point. But if you take the entire picture, right, of the entire function, it's not the highest of all max values. So this is technically the graph now that you can maybe make into a 3D case, right, and then have some. Now they have something similar in a textbook. I believe they're trying also to show off in their one of the saddle points. But again, absolute max, absolute mean are the absolutely highest or lowest points in terms of z-value. And then you can relative mean and relative max if there are higher values than that value. So that would be that. And now we are going to say that the min or max or saddle point happen at those points which make partial derivatives 0. So if this is a theorem, so if f of xy has a min or a max at AB and partial derivative fx and fy exist at AB, then partial derivative xy is the same as partial derivative y. Sorry, not xy, AB. You have to compute everything at AB. So AB is going to equal to 0. Now, you are used to saying set derivative equal to 0 to find critical points. Well, actually, we will see later. It actually comes out from the calculation. All right, great. So now, these are critical points. At AB. Number 1, fx AB is the same as fy AB, exactly what we had up there, equal to 0. Or 2, at least 1 of the partial derivatives is or does not exist. So critical points, just like in Calculus 1, happen when the derivative is equal to 0 or if the derivative doesn't exist at that point.
That would be the equivalent of like when we had like the graph of the absolute value of x, right? The x equals 0 would be.
Perfect. It's a spike. So you have the two slopes competing at the same point, -1 and 1, and you can't have two different values at one point. So derivative doesn't exist, and that would create the critical point. Yes, very good.
So the equivalent for that in 3D is just a point where, I mean, if it were happened to be.
Well, just a corner of the desk.
Okay.
All right, because the limit doesn't exist at that point, and so on. So there are, you know. Now, very important, guys, second derivative test, because this is where that formula is I told you about earlier. Second derivative test will determine which critical point is minimum, which one is maximum, and which one is saddle, and then if the method fails altogether. So let's take a look. So the second derivative test. So the second derivative test says, suppose that the second part of the derivatives are continuous throughout the open disk centered point AB, and then derivatives are 0. So suppose that the second partial derivatives of f are continuous on the region with fx equals fy equals 0. Let d, which is some type of a discriminant over here, is going to be fx computed, well, fxx xy times fyy xy minus fxy squared at xy. This is the formula that you will use a lot. That was a confirmation. And now we have cases. Number 1. If d computed at AB is larger than 0 and fxx is less than 0, the point is max. Let's do AB is a max. So AB is a max. Number 2. DB larger than 0 and fxx larger than 0. Then in that case, AB is a min. Number 3. DAB less than 0 means AB is a saddle point. And number 4, DAB equal to 0, test is inconclusive.
I don't remember the last time I tried to spell the word set. So, just making sure.
And that only has fx minus, not the second.
Yeah.
It doesn't mean fx.
What happened? Now, these problems tend to be a lot of work. You need first partial derivatives, then the second partial derivatives, then the mixed partial derivatives, then you have to set first derivatives equal to 0, obtain points, compile the D formula, and then run that as well, and then, you know, it could be a very long process. Especially because of equations that you have to solve, the system of equations. So let's see something from the homework that is not going to take us 30 minutes to do. That's going to take forever. I'll go with the analog book.
We have one of these long ones on the exam.
Yes. It was like your problem 10, right? You have to have something that will that will hurt.
We haven't had any lab days left.
Remember when Rob said you just need to double make sure that
How much?
well, yeah, and I was like, but Rob is just a lie. Like, what chapter was that, Rob? I've been focusing
Today?
so I got it.
Said something kind of like this. I'm probably gonna. I might work on that today.
All right.
On Friday.
Yeah.
Here we go. Problem
Oh yeah. I see that now.
Let's go with something cheap first. X to the 4 plus y, guys. I'm trying to fit the problem and the formula and the conditions all on the same page. So the problem is x to the 4 plus y to the 4 minus 4x minus 32y plus 10. If the computer doesn't load, so I can quickly jump there.
We're finding the.
Don't you pick the non-one to give the answer?
You want us to find if it's what before you want us to find?
So you are going to find critical points by setting the first partial derivatives equal to 0. You will find critical points. Then you will find the other partial derivatives. The second partial derivative is going to compile the D formula. Now your critical points that you found, those will be your A and B one at a time, and you test them all. Some of those will be min, some will be max, some will be inflection, depending on stuff. See you in 30 minutes. I'm just kidding.
You're not though.
So we just take the first derivative.
Yeah, just take 5 derivatives, yes. Take 5 derivatives. 2 first, 2 and 3 second. Right? Because you have mixed derivatives.
Once you have the critical points, you put that into D. Right, don't look like that.
Wait, I don't think
Yes, the second.
Yeah, so you want to just figure that out? No, I already have it. Yeah. What's the oh, yeah.
Okay, yeah. Oh, and that's math.
You got this. Juan, you got this.
I have a question. Okay, so is this actually
That's 0.
That's why
is the y squared, or did I write that?
Yeah.
So once you find it, you square it all. You see the first part is fxx times fxy. And the second one is fxy squared.
That's like, are we only supposed to do one critical point? Is that all I
It could be up to 16 and 30 and 70. Depends on the problem.
I don't know. I haven't found the problem.
You found one test set, one you find.
Yeah, that's what you're supposed to square.
Maybe that's all there is.
Don't we need a point? Is there a point to see?
No, there's no point.
Oh, like x, where x is 0.
Oh, because you have to find the
the
critical.
4 of a point.
Like where you're at x is 0. First part, x partial derivative and y partial derivative.
Would f of x
Plug in.
Well,
f of x
x is 0, y
y
is
equals 0.
f of x y would be 0.
Yeah, fxy is 0.
Yeah.
first derivative or the
So,
second?
Are we just basing for the formula?
You got y equals you plug those numbers in.
Yeah.
D equals
Yes, it says here 5. 4 times 12.
First one, x is equal to 1.
Did anyone get more than one critical point? Because I got
What are x and
No, that's
they aren't AP values, they're where you're plugging in the actual
Yes. Ryan has these
Y is equal to
Then.
Yes, there is only one critical point in this case. It's 1, 2.
That's what I got straight one. And everyone else gets like the minimum. That's what I got.
Now we're going to.
dash is some side.
So now we're going to compile the D formula, and that's going to be fxx, which is 12x, times 12y minus 0 squared.
I think the fxx and fyy are 12x squared and 12y squared.
Yes, I said that. So now we have 144 x squared y squared. So that's our capital D. So now you can see immediately that D is going to be positive, because when you plug any numbers for x and a y, because they're both squared, it has to come out as a positive number. So D computed at 1, 2 is going to be 144 times 1 squared times 2 squared. So that's what I thought. 576.
I thought that it was a minimum.
Now we see that we have that D is larger than 0. And we also have that fxx is doing what? Fxx at 1, 2 is going to be fxx is positive, right? So it's also positive. So when they're both positive, you get a minimum. Now, please pay attention to my answer. I said minimum at 1, 2. I didn't say minimum is 1, 2. So what's the issue? Why am I saying minimum at rather than minimum is? There's no z. I didn't compute what minimum is. Remember, z value is the elevation of the function, right? Where the stuff you are walking on z equals 0, ceiling is z equals 10. Those are all z values, right? Z equals f of xy. So we know it's a minimum. Now you can go back to original equation, plug in 1 and 2 and get the z, and then you will know what the minimum value is. And then you will say 1, 2, whatever you get. And then that would be the full answer, because you want to compute. So now need to compute z, because that's going to be f of 1, 2. So now what do we have? We had 1 to the 4th power plus 2 to the 4th power. Now who picked this problem? It's forever. Oh, okay, don't worry about it. So z is equal to 1 to the 4th plus 2 to the 4th. Then what? Minus 4 times 1. And then plus 32 times 2, right? No, minus 32 and then plus 10. So now we have 1 plus 16 minus 4 minus 64 plus 10. Let's say it's good. So minimum is 1, 2, negative 49. And that's the answer. So there's a big difference between saying minimum is and minimum is at, right? Because at is just the wording that says, all right, for which point in the domain I have a minimum now.
I can make it 41.
Me as well.
Oh,
So,
Deserved it, right? Good. There we go.
So if it was less than 0, like could the value you would say saddles?
And you walk away. Yep.
Yeah.
So if you get multiple critical points, that's all.
Yes, because some of them are min, some of them are max.
Question at that. So if you're solving point, do you still solve for Z?
Yes, because that also happens at the point, right?
Because you don't want play.
You always solve for z to present the whole point, because 1, 2 is just a location, right? If I label this point here as 1.2 and I stand on it, right, you have no information of my height at that point. You just know where I'm standing, right? This is the max right here. We will say 6,1, right? That's what the max point is. So location, and then you have to compute z value to see what that actually is. Good. So that's that. There's much more, obviously. So this is this problem only. Let's see what else we can find. Beautiful.
I did. Oh God.
All right. So now we are going to work on optimization problem for packaging engineering, let's say, or airport regulations or whatever. So what you have is a packet which has the, we're going to call this the height or the length. So this is called the girth over here. And then you are going to add this side to it. So now the problem says that so the height of the packet, right? Because guys, you're going to stand this packet, right? This is the base of the packet. The one that I outlined blue is the base, and you would stand it up so that this other blue edge is the height. So it says in the problem that the girth plus the height is not to exceed 96 inches, right? So those are the shipping regulations. So if I label these as x, y, and the height, I have 2x plus 2y plus a single edge not to exceed 96. So we are just going to say equal to 96, right? What is the maximum volume? Right? So we want the maximum volume, and we have these restrictions. So there is nothing else that is given to us, right? In Calculus 1, we might say it's a square base because we have to eliminate a couple of variables. But over here, the shipping company handles rectangular boxes provided that the sum of the height and the girth of the box does not exceed 96. Find the dimensions of the box which meets this condition and has the largest volume. So this is all we have. Now, what else do I have here? Where I have the volume, actually, I can write the volume. What is the volume for this box? Very good. And we need that to be max. So now, what I'm going to do is I'm going to solve in the upper equation for h and plug that in the volume to eliminate one of the variables, and then just unleash the method to get extra. Yes, unleash the method of partial derivatives and everything else. So from the top equation here in green, I want to do the green. Shush.
Orange.
Indigo. That's gonna stick.
What?
Indigo. I will. Yeah. Volume is xy times 96 minus 2x minus 2y, and that equals to a max. So now we distribute. That's 96xy minus 2 times, so 2x squared y minus 2xy squared equals to max. And this is actually our equation. If you remember anything from Calculus 1, the procedure so far is identical. You have two equations, you plug one equation into another, but you have the constraint and you have objective equation. Objective of the problem is to maximize the volume. So that's the one that you will be differentiating. Constraint is the one that provides relationships between variables so that you can eliminate some of the variables. And that was the one with the 96, right? So now, when we plug everything in, we get this long equation here, and now we finally do the partial derivatives. So fx is equal to 96y minus 4xy minus 2y squared. Yeah, equal to 0. Good luck. The next one is fy. So 96x minus 2x squared minus 4xy, also equal to 0. So now, please stare at these equations, because this is a moment when you should learn and remember that when you have equations like this, they are symmetric. And immediately when you have symmetric equations like this, that means that x equals y. They're the same. Look. You see, this is negative 4xy, negative 4xy, negative 2y squared, negative 2x squared. So, and this is x and y. So if you swap all x's with y's, you get the same equation, right? If you interchange x for a y and y for x, you get the same equations back. That's called symmetric. So, when we have symmetric equations, guys, you should be writing this down, because if you run into symmetric equations and try to solve this, it's going to take an hour. Right? So when you see symmetric equations, your immediate conclusion is that x equals y. This is going to save your life in the next section with Lagrange. When we have 3 equations and 3 unknowns, or 4 equations and 4 unknowns, and you get the symmetric set. You get the symmetric set that's immediately cause for celebration, because you just knocked out a variable. So now, I'll write here in blood, these are symmetric equations. So, x equals y. Great. Now that I know that x is equal to y, I can just pick any of the 2 equations and replace all y with x's and just solve that. So, if I pick the top one, I'll just say 96x minus 4x squared minus 2x squared equals to 0. So this is now 96x minus 6x squared equal to 0. I'm going to factor out 6x. And what's left over here is 16 minus x equal to 0. X equal to 0 is the solution that I have to drop. Please remember that we are looking for dimensions of the box, and a dimension of one side is x. Does the box exist if the length of the side is 0? No, right? So that's the garbage answer. You throw it away. Also known as extraneous solution, but garbage answer is just fine. And then the second one is x equals 16. Sure, 16 inches, that makes sense. And then immediately I know y is also 16 inches because x is equal to y. And now I can go and use the constraint equation all the way on top to figure out age, right? So age, which is the height, is going to be 96 minus 2 times 16 minus 2 times 16. That is 96 minus 64, which is 32 inches. So dimensions for max volume are 16 by 16 by 32 inches. And that's the package. So make sure you are on the lookout for symmetric equations. This was a word problem, 35. Now you have also 36, 37, 38 to practice your skills. And then you'll definitely have some stuff online. So it is important for you guys to realize
I was going to say that.
And now the grand finale. Yes. So, okay. I hope you are familiar with the concept of a cookie cutter. So, behold the dough, right? You are going to make cookies out of this dough. Now, dough on the top is wavy. This one right here. It's wavy. So it's going to have a lot of these min and max values and saddle points, right? So everything. Now, it is not an infinite dough. It's going to be bounded in a region. Well, that little piece that creates a cookie is going to be bounded when you hit it with a cookie cutter, right? It's going to have a finite region of space that it takes, right, in the domain. So, when you have a finite amount of dough, right, or when you are on restricted domain, then you can talk about absolute min and absolute max, because you will be able to find all points that are min and max on that interval, or on that region, and then you will be able to take a look at all of the z values and pick the highest z as absolute max and the lowest z for absolute min. Now, obviously, when you are thinking about a certain region, so when you cut out a cookie, or whatever shape the cookie is, it could be, you know, the circular cookie, it could be the square cookie, the rectangular cookie, the triangular cookie, whatever kind of cookie cutter you press into it, the cookie will come out with the shape of that cookie cutter. Now, as I said, it's the finite object which has a finite amount of min and max values, and we can find all of them. Now, observe that all of the points that are inside, which are interior points, will be covered by the method that we just did. The only other points that we have to work out, and it's different, is the boundary. You see, if you take a look at this microfiber cloth, you can, depending on if you ate beets and carrots as kids, right, if your eyesight is good, you can see the seam at the end. Now that would be the boundary line. On that boundary line, and we have 4 in the case of this microfiber cloth, right? I have 4 boundary lines. We are going to have min and max values possibly on those boundary lines as well. There is a new procedure to calculate that. The inside, so everything inside is going to be calculated with the method we did so far. And then you will have to have additional 4 calculations to figure out min and max values at the edges. Now, what happens at the edge, actually, is you are getting an equation that describes that edge, and then you are actually casting a problem into Calculus 1 because you will be eliminating all of the variables and you will be left with one variable only. So, if this is the problem that I'm solving, I have to do everything we just did to figure out the inside, and then I have to do 4 Calculus 1 optimizations around to figure out all min and max values at the edge. You cannot have a saddle point at the edge. That should be common sense. You can have saddle points inside, but you can't have them at the edge. So let's take a look at the problem. Now, these problems tend to be very long because we just did this problem, and that's just the inside. Then I have to do additional 4 problems, right, if I have the square or rectangular one, to calculate the edge. Now, all of the, as I said earlier, all of the min and max values are put on a pile, and on that pile, one of those will have the highest z, or maybe 2 at the same time, whatever. All of them are absolute max, and then 1 or more will have the smallest z, which creates absolute min. So let's dive into this problem. We only have 17 minutes, so let's... Fine. I was going by that clock over there to buy minutes.
What's time?
So let's take a look at problem 46, because we can. All right, so cookie dough has the equation of 6 minus x squared minus 4y squared. Now, this is actually elliptical umbrella because this is the x squared and the y squared have a different numbers, so it's elliptical. And now the region R is described as set of all xy points such that x is between a negative 2 and 2, and y is between a negative 1 and 1. So that's our information. Well, we are going to quickly plow through the middle first and then deal with the edge. So fx is going to be 6 minus 2x. And negative 2x. Yes. And then negative, I'm just making sure you're paying attention. And then negative 8y, so that's fx. Now I need fxx, that's going to be negative 2. fyy, negative 8. fxy equal to 0. Yes. Now, if I set both of these equal to 0, I get negative 2x equal to 0, so x is 0. And negative 8y equal to 0, y is equal to 0. So the only point that I have is at 0, 0, which is the origin, right? Now, if I want to calculate the point, it's 0, 0, 6, right? When I plug in zeros in original equation, I get 0, 0, 6 as a point. But currently, I just worry about the denominator. All right, so now big D is going to be negative 2 times negative 8 minus 0 squared, which is 16. Now, that's always bigger than 0. And what do we know when this is bigger than 0? Either min or a max. So now we look fxx, and fxx is negative. It's a max. Now, we should know that this is a max, right? Because I told you it's umbrella. An umbrella has a maximum point on top, right? This is elliptical umbrella. You open the umbrella and you squish opposite sides a little bit in, right? So the other two pop out, and that's where the 4 is. And wherever you squished, that's when the x's are, right? You squish on the x and the other ones pop out. So it's elliptical umbrella. Great. We just proved that that elliptical umbrella has a max value. Now, I can't claim absolute max or relative max because I have to see what's happening at the edge of this problem. Now, we are going to now go into the second part of the problem. So I'm just going to, since there was a popular demand, I'm going to use purple. I don't think I can do indigo over here. Oh, they write indigo. It's purple. Okay, thank you.
Indigo's gold.
Did you know that my blue is different from your blue?
I know.
Does it matter if you call it blue?
All right, so
Exactly.
what's new?
Indigo is different than his indigo. And different
Look
than whoever made this program.
at the edges. So look at the edges. What do I have at the edges? I have the domain, which I need to draw. Make sure I understand that domain. The domain says negative 2 to positive 2 on x-axis, and then negative 1. So it's a rectangle that goes negative 2, positive 2 on x, and negative y, positive y. So this is region R. That is region R. Guys, this is the cookie cutter, all right? So observe that the domain for your function up there is infinite. You can plug in any x and any y you can possibly think of. So that domain over there is negative infinity to infinity by negative infinity to infinity. So that is infinite. It goes forever. What I'm going to do is I'm going to hit it with the cookie cutter over there and just look at the piece. Now, as you can see, this cookie cutter that we are using is actually surrounding the origin at which we have 0, 0, 6 as a max. So if any of the sides works out to have a z value bigger than 6, then that would be absolute max. If 6 is the biggest one, then 6 is the absolute max. So we'll see that. Now let's consider these equations here. I have the f of xy given as 6 minus x squared minus 4y squared. And now I am going to just label this 1, 2, 3, and 4 for 4 calculations that I'm going to do. Calculation number 1 is going to have equation y equals to 1. I hope you see y equals to 1 equation up there because it's a horizontal line, right? Plug in. And you see that your equation now collapses into f of x because now I have 6 minus x squared minus 4, which is 2 minus x squared. Guys, this is 2 minus x squared. I can optimize this quickly. So f prime of x is negative 2x equal to 0. And I have that, I have my max value at 0 and 2, right? Oh, hold on. I did this bad. I wrote it bad. So let's do this first, and then I'll say x equals to 0. Sure. We know that y is equal to 1. And then when you feed all of that into this equation or the original one, you will get that your z is equal to 2. You can put any, yeah. You can put in the original equation over here, right? Or you can just use this equation to calculate your z, whatever. So now we found another point, which is 0, 1, 2. Now we know that the 0, 0, 6, right? 6 is larger than 2, so far that's winning. That's okay. Let's go calculate the second one. Now for the second one, I have that x is equal to negative 2. Plug in. So x equals negative 2. I have that my now f of y is equal to 6 minus negative 2 squared minus 4y squared. That's a 4, not a 6. And now when you solve this, 6 minus 4 is 2 minus 4y squared. F prime of y is going to be negative 8y, set it equal to 0. We are getting, we know that x is negative 2, y is 0, and z is going to be, what is z? When I plug in over here, 2, right?
Wait, how do you do that?
Plug in the z equation. This is equal to z, right? Number 3, y equals negative 1, but then that's getting squared, so same as 1. So we should have 0, negative 1, 2, and 4x is equal to positive 2, so same as 2, and we get is that 0, 2, 2? I hope.
2, 0, 2.
Oh, x is 2, yes, 2, 0, 2, thank you. 2, 0, 2. Observe that all z values are 2. Absolute max, no, at 0, 0, 6 at the origin. Wow, that was 10 minutes. The whole problem in 10 minutes. Because I skipped those calculations I just said same, where you would actually grind through that. Looking at some other problems, your boundary is a circle. X squared plus y squared less than 1. The interior of that circle. You will use equal to 1 in your calculation. So you are plugging that in. So you will solve that one for, let's say, y squared equals to 1 minus x squared, and you will replace y squared with that. Or if you have x squared in the equation, you will replace x squared as 1 minus y squared. So it's just, it's the game of plugging in correct values where they go. Tomorrow, we can kick off with one of these problems to warm up, and then do lots of Lagrange problems.
Okay, I have a question
Sure.
for you.